So this is now part B of the screencast for chapter 16 on capacitors. So chapter 16, part A was on the electric potential, and part B will be on capacitors. So you should be taking notes as I go along so that you'll have the equations written down in your notebook that you'll need for the long kappa problems. So let's start with an introduction. In general, a capacitor means a system with two insulated conductors which have equal but opposite charges, say plus Q and minus Q. So for example, it could be two spheres or just two conductors of any shape. This is the general meaning of the term. Now remember, a conductor is an equipotential. So all points of the conductor have the same potential. So let's say the negative charge has potential V1 and the positive charge has potential V2. And then the potential difference is V2 minus V1. All right, well, that's a very general example. Remember, the electric field flows throughout a region of space from high potential to low potential. So the positive charge will be high potential, the negative charge will be low potential, and the electric field will flow, it has this shape, from the positive charge to the negative charge. Now we define an observable or measurable quantity called capacitance of this system, denoted by C. It's Q divided by delta V. That's simply a definition. And now, since that's an observable quantity, it has to have a unit of measurement. The unit of measurement is called the farad, named after the famous physicist of the 19th century, Michael Faraday, denoted by capital F, or abbreviated by capital F. And what's the unit? It can be expressed in terms of other units in this way. Charge is coulombs, and potential is volts. So 1 farad is 1 coulomb divided by 1 volt. All right, we've described what's meant by a capacitor and the capacitance, but that was a very general definition or description. Two conductors, two insulated conductors. In other words, they're not in electrical conductivity, electrical contact. But now let's get a little more down to earth. In practice, a capacitor is a circuit device found in many circuits, electrical circuits. It often takes the form of two plates or metal foils, and those are the two conductors. They're metals. And they're separated by an insulating material because they have to be insulated from each other. They could be separated just by vacuum, but that's not very likely because then it would be very difficult to keep them apart. In a theoretical or kind of conceptual description, you might say, well, there's nothing between the plates except empty space. Or you could say air, which is hardly different from empty space as far as electricity is concerned. But again, being more concrete about it, usually there's a material between the two plates which has the effect of preventing electrical contact. It would have to be an insulating material. That's what we usually call a dielectric material. It could be glass, or it could be something flexible like plastic, or even paper. Paper is basically a non-conducting material. So it depends on the design and construction of the conductor. Now this is called a parallel plate capacitor. Two plates, two parallel conducting metallic foils separated so that they're not in any electrical contact. There'll be some geometrical parameters. There'll be area A and separation D. So this distance is the separation between the two plates, D. And the size of the two plates, normally they would be of the same size, is the area A. And one will be positively charged with a higher potential V2. The other will be negatively charged with a lower potential V1. All right, so that's a parallel plate capacitor, and most of our calculations will concern parallel plate capacitors. Now I define capacitance as Q over delta V. All right, for this geometry, what is that capacitance? In other words, what's the capacitance of a parallel plate capacitor? The definition of capacitance is the charge over the potential difference. Now, the potential difference will be proportional to the charge. So the ratio between the charge and the potential difference will not depend on the charge or the potential difference. The potential difference is proportional to charge. So when I divide charge by potential difference, the charge cancels out. It doesn't depend on the charge. What does it depend on? Well, it'll depend on these geometrical features, A and D, and it'll also depend on what material is between the two plates. So let's start with the idea that there's nothing between the two plates, or maybe there's just air between the two plates, and we can neglect the dielectric properties of air since they're very small. Then the capacitance of the parallel plates is epsilon naught A over D. So you see, the capacitance doesn't depend on the charge and the potential. The capacitance is something intrinsic to the design. It doesn't depend on how it's charged. It just depends on the size and shape. In the case of a parallel plate capacitor, the size is given by the two parameters D, separation between the plates, and A, their area. Now this is the definition. This is the case of parallel plates. Of course, if I had not parallel plates but two spheres, the capacitance would not be given by this equation. This is the equation for parallel plates. And now let's prove it's correct. We have to prove it from the definition. So we'll start with Gauss's law. Gauss's law says that the electric field between the two plates, remember this is a high potential, so there's an electric field pointing this way on all points between the plates. There's a little bit of electric field outside of the volume, but that's small. If the two plates are close together, the electric field is concentrated in the volume between the two plates. So we'll make that approximation. We'll say that mostly the electric field is between the plates. And by Gauss's law, it's the charge density, let's say on the lower plate, so we'll call that sigma, divided by epsilon zero, where epsilon zero is that parameter, that electric parameter called the permittivity of vacuum. Remember, we had an equation for the electric force in terms of the Coulomb constant, Kc, but we also define a constant epsilon zero, which is called the permittivity of vacuum. So E is the charge density divided by epsilon zero. That's the electric field between the two plates. It should be a vector. Well, it points from the positive side to the negative side. That's the vector. This is the magnitude. Sigma is charge density. So sigma is charge divided by area. It's the charge per unit area. If I took a little area here and I measured the amount of charge inside that area, it would be the area, delta A, times the amount of charge inside there, times sigma, would give me the amount of charge inside there. Now, that's one equation we have for the electric field. And that comes from Gauss's law. If I set up a little Gaussian surface here, the electric flux through a Gaussian surface would be equal to the charge enclosed divided by epsilon zero. So Gauss's law says flux is the charge enclosed by an imaginary surface divided by epsilon zero. Okay, so the imaginary surface I'm going to take is a little cylinder cutting through one of the plates only. Well, there'll be flux for the part of the cylinder inside the volume, and then the charge enclosed will be sigma times the area of the ends of that little cylinder. So the flux is Q over epsilon zero. Q is sigma times A. The flux is E times A, so the A's cancel. And so E is just sigma over epsilon zero, or Q over epsilon naught A. I guess the easy way to see it is that the flux is E times A, and that's equal to the charge over epsilon zero. So E is the charge over epsilon zero A. Now, I have another equation for the electric field in terms of the potential. Remember, the electric field is the negative rate of change of the electric potential. That was from part 1 of the screencast. The change in potential per unit length, that's the rate of change of the potential, is equal to the electric field. No, that negative of that is equal to the electric field. So in this case, the electric field is the change in potential, that's delta V by definition, divided by the distance between the plates is D. So from the relation between electric field and electric potential, E is delta V over D. And now if I want to solve for C, I have Q over delta V. Well, Q on the one hand is epsilon naught A times E, and delta V is D times E. The E cancels, so I just end up with epsilon naught A over D. So that's the proof of this relation, capacitance of a parallel plate capacitor. Now again, epsilon 0 is the permittivity of vacuum. So this would correspond to two plates separated by vacuum, empty space. The value of epsilon 0 is 1 over 4 pi k. K is that Coulomb constant from Coulomb's law, roughly 9 times 10 to the 9th in SI units. This turns out to be 8.85 times 10 to the minus 12, and then the unit. Now what is the unit? Well, I could write the unit in terms of coulombs and volts and things like that, but I can also write it in terms of farads, because you see here, C is farads, A is meters squared, and D is meters. So farads per meter is epsilon 0. So for the purpose of calculations with capacitance, it's useful to write epsilon 0. The permittivity is 8.85 times 10 to the minus 12 farads per meter. You could re-express that in terms of coulombs and volts and so on. Now this is something that you will need for the long kappa problems, because there'll be some problems where you have a parallel plate capacitor and you'll need to know what the capacitance is. All right, but now let's go on. Here's something more you'll need for the long kappa problems. What happens when you connect capacitors in series or in parallel? So suppose we have two capacitors. You know, we'll indicate a capacitor like this. We'll say it's got a plate with positive charge. It's got a plate with negative charge. So here's Q. And here's minus Q. That's a capacitor. And you know, we could have a capacitor which is not in the form of a parallel plate, but of two parallel plates. But anyway, that's the way we'll indicate a capacitor in a circuit. Now here's a circuit with two capacitors and a battery. So the battery has some electromotive force or some voltage. For example, a D-cell battery, a traditional D-cell battery, has a voltage of 1.5 volts. And it's connected to two capacitors in parallel. So what do I mean by parallel? I mean, it looks like these two capacitors are this is in series. So this is not in parallel. This is series. This is parallel. What is meant by series is that there is a wire going from the positive terminal of the battery to one capacitor, then a wire from that capacitor to the other capacitor, and then a wire back to the negative terminal of the battery. So, in other words, there's a circuit, there's a loop, which goes from the positive terminal through both capacitors, one first and then the other one, and then back to the negative terminal. So you see, they're in series. The circuit first goes through capacitor number 1 and then through capacitor number 2. They're arranged sequentially. This is parallel capacitors. Again, we have a battery and it's connected to two capacitors. But the connection is different. They're actually two parallel paths. There's a circuit which goes through capacitor 1, and there's another circuit which goes through capacitor 2. So capacitor 1 and capacitor 2 are connected in parallel. They're both connected to this point, and they're both connected to this point, but the circuit does not go first through C1 and then through C2. They're not sequential, they're parallel. All right, it turns out, well, the simple one is the parallel case. The combined capacitance of two parallel capacitors is the sum C1 plus C2. So if you have this arrangement, it's like you have one big capacitor with capacitance C1 plus C2. Whereas in this case, the combined capacitors are equivalent to one capacitor with capacitance 1 over C1 plus 1 over C2. In other words, to get the combined capacitance for capacitors in series, we add the capacitances, we add the reciprocals of the capacitors. We don't add the two capacitances, making a big capacitor. We add the reciprocals of the two capacitors, which actually in the end gives us a smaller capacitance. So what about the charge? Well, for capacitors in series, the first capacitor has charge Q and minus Q. The second capacitor has charge Q and minus Q. Same charge, or same charge difference on both capacitors. Why is that? That's because if you look at this part, let's see if I can blow this up a little bit. And if you look at this part, the lower plate of the top capacitor, the upper plate of the bottom capacitor, and the wire, that's one conductor. It's two conductors connected by a wire. It makes one conductor. That has charge 0. So if the upper plate, if the other upper capacitor has charge Q1 and Q2, Q plus and minus Q1, and the lower capacitor has charge plus Q2 and minus Q2, Q1 minus Q1 plus Q2 has to be 0. In other words, Q1 and Q2 have to be the same. Another way to look at this is to imagine when you first connect the capacitors, some current flows from the battery to the top plate of C1 and from the bottom plate of C2 back to the battery. Nothing flows to the other two plates because they're insulated. See, these two plates are insulated from plus Q and minus Q, from the terminals of the battery. So these have to remain with charge 0. The charge can be separated into minus Q on the top side and plus Q on the bottom side, but the total charge has to still be 0. So the charge on the top plate of C1 is Q, the charge on the bottom plate of C2 is minus Q. The charge on the upper capacitor will be plus or minus Q. The charge on the lower capacitor will be plus or minus Q. Now, when I say this is the series capacitance, the inverse of C1 inverse plus C2 inverse. The reason that is because Q is that series capacitance times the voltage of the battery. The voltage of the battery is this voltage, which is Q divided by C1. Remember, voltage is charge over capacitance. So this voltage is Q over C1. This voltage is Q over C2. And the combination is the voltage of the battery. So Q over C1 plus Q over C2 is Q over C of the series. So therefore, we add the reciprocals of capacitance. Now, on the other hand, for parallel plates, the first capacitance will have charge plus or minus Q1. And the second capacitance will have charge plus or minus Q2. And Q1 and Q2 will not be equal. What's equal is the voltage, the two voltages. VEMF and VEMF is the voltage difference across capacitance C1 and capacitance C2. So the total charge on the upper side is Q1 plus Q2. And the total charge on the lower side is minus Q1 minus Q2. So the upper charge, Q1 plus Q2, is the parallel capacitance times the voltage of the battery. So Q1 is C1V, Q2 is C2V. The right-hand side is C parallel times V. The V's cancel. C1 plus C2 is C parallel. All right, well, all of this is explained in section 16.4, and you're going to need that for the law and kappa problems. So these are the basic equations. You should write this down in your notebook. But you should read section 16.4 to make sure you understand that. Another quantity that you're going to need for the law and kappa problems is the energy in a capacitor. A capacitor is a circuit device that stores charge and stores energy. So let's figure out how much energy is in a charged capacitor. We'll call it U. Let U be the energy stored in a capacitor where the capacitor has charge Q, or rather separated charges plus and minus Q, and potential difference delta V. So given those two quantities, what's the energy? Now, we attribute this energy to the field. In other words, this energy does not belong to the charges. This energy belongs to the electric field. So we refer to this as field energy. All right, well, to derive the formula, and here's the formula. The formula is rather simple. But to derive it, we think of a capacitor, think of it as two plates. And suppose the charges are plus Q. Let's put that one down here. And minus Q. Let's put that one up here. So suppose the charges on this capacitor. So this is the capacitor. This is C. Suppose it has charges so that's the capacitance. Suppose it has charges plus Q below and minus Q above. You could do it either way. Now suppose I want to move additional charge from the lower plate to the upper plate. So suppose I want to move from here to here an additional charge delta Q. No. Well, remember the definition of potential energy. Charge times the change in potential is the change in energy. So, I think I have this explained wrong here. This is wrong. I want to move charge from the negative plate to the positive plate. I have a little misprint here. In other words, I want to increase the charge separation. I want to move a little positive charge, delta Q, a little amount of coulombs, from the negative plate to the positive plate. So that will increase the charge on the lower plate by delta Q, and it will decrease the charge on the upper plate by an amount delta Q. So after I make this change, this charge will have this plate will have charge Q plus delta Q, because I added that charge delta Q, and the upper plate will have charge Q minus delta Q. No, it'll have charge minus Q minus delta Q. Okay, so I'm increasing the charge separation. What's the change in the energy? Well, you have to remember the relationship between energy and electric potential. The energy change is the amount of charge times the voltage difference from the lower plate to the upper plate. In other words, delta V. This plate has charge V1. This plate has charge V2. V1 is larger than V2 because it's the positive plate. So I've moved an amount of charge to the higher potential plate. The amount of energy is the charge times the change in potential. Now the potential difference when I move this charge is Q over C. So before I move this charge, the plates have charge minus Q and plus Q, and voltage difference delta V, which is Q over C by the definition of capacitance. Remember, capacitance is Q divided by delta V. So delta V is Q divided by C. Now, the change of Q times Q is the change of Q squared divided by 2. So the change of some quantity x squared, if I change x from x to x plus dx, is 2x times the change in x. This is very familiar in calculus, but calculus is not a prerequisite for this course. So let's see how that can be. Suppose x is 1 and dx is, let's say, 0.01. So I change x from 1 to 1 plus 0.01. Well, then how much does x squared change? Well, I have, if I expand out this square, I have 1 squared, so that's 1. Plus I have 2 times 1 times 0.01, so that's 0.02. I'm running out of space here. .02. And then I have 0.01 squared. But 0.01 squared is only 10 to the minus 4. So I'll neglect that. That's a very small number. I mean, that's only 1 part in 10,000 compared to 1, whereas this part is 2 parts in 100. So delta x squared is 1, which is x squared, plus 2 times delta x, which is 0.01. So this is an example of that relationship. It says the change in x squared is 2x times the change in x. So the change in q times q is the change in q squared divided by 2. Now, of course, when I make this change in the charge, the capacitance does not change because the capacitance doesn't depend on the charge. The capacitance just depends on the area and the separation of the plates. So the capacitance is a constant as far as Q is concerned. So the change in the energy when I move this charge delta Q from the negative plate to the positive plate is the change of Q squared over 2Q. Well then, the energy must be Q squared over 2C. So that when I change Q, the change of U would be the change of Q squared over 2C. Or I can rewrite it in terms of the potential. Remember, Q is C delta V, so Q squared is C squared delta V squared. Then I divide by 2, and I divide by C. So I'm left with 1/2 C delta V squared. So these equations, I hope you're taking notes. You should have written in your notebook these equations for field energy in a capacitor. There are 2 ways you can calculate it. You can calculate it from the charge, it's Q squared over 2C, or you can calculate it from the potential difference. It's 1/2 C delta V squared. Now, of course, you don't need to know the derivation in order to solve the long kappa problem, but you do need to know these 2 equations. So you should have those written down in your notebook. All right, well, that completes chapter 16. And you should still read chapter 16 because there's more detailed information in the book than there is in this little short video. But this should give you the equations you need to start doing the long kappa problems.